Hello and welcome to the MOOC on optical communications. In this module we will discuss some aspects of noise associated with optical amplifiers. We will talk about the signal and the amplified spontaneous emission noise beating, and we will also talk about the noise because of the amplified spontaneous emission beating with itself. Okay. We will evaluate the noise figure of an optical amplifier and show that for an ideal optical amplifier the noise figure turns out to be 3 or rather 3 dB. Okay. So, let us look at, before looking at the noise in the optical amplifier, let us put down the setting that we are interested in. So, we know that from the transmitter side you are actually getting an input signal. Okay. This could be modulated waveform or it could be just a constant. Now, we will simply assume that the input signal that is coming in has a certain form which is given by some power. Okay. And this power, so we are going to use a slightly different notation that we have used. So, here we will assume that the amplitude of the signal is under root of 2 into p. This of course is centered at the optical carrier, which is Fc. So, cos 2 pi Fct, the carrier has a certain random phase theta. Okay. This expression could very well tell you the pulse that you might have received when you are transmitting using a on off keying system. Okay. When you transmit a pulse, okay, then the amplitude of the pulse would be square root 2 p, and then it of course has a certain center in terms of the frequency, it will be centered at the frequency Fc. In the previous classes we might have used Fs is equal to Fc. So, we might have just used a different notation. Here we are using this notation of Fc. The information is actually residing in the power and not really in the phase of the information. The phase is completely random. It could be anywhere between minus pi to plus pi. Okay. So, this is my optical signal which is arriving at the receiver. What we do here is that we take this one and then send it through a amplifier. Okay. The amplifier is assumed to have a gain G, and there are certain noise processes that are associated with the amplifier, which we are anyway going to talk about it slightly later. After you have amplified it, you then filter it out. Okay. So, this filter is actually implemented as a band pass filter in the optical domain. So, please note that the signal that you have received is optical. After amplification, the signal still remains in the optical domain. That is because you are actually using a optical amplifier. Optical amplifiers amplify signals in the optical domain, and once you have amplified the signal in the optical domain, then you are filtering again in the optical domain. Okay. After you have filtered that in the optical domain, you are going to put this one through a photodetector. Okay. So, that you may convert the optical signals into electrical signals. You might also want to put up some electrical filters here in order to limit the out of band noise, or the electrical filter could be part of the transimpedance amplifier design that goes with the photodetector itself. And what you get at the output would obviously be the signal or the photocurrent that you are interested in. Okay. The filtered photocurrent is what you are going to get, and whatever the processing that you want to do, you can do the processing onto this photocurrent. Okay. So, this is our model. Now, let us first write down what would be the signals that you are going to see at different points on this chain, and then look at the statistics of the noise processes that go along with this. Okay. Now, to see that one, let us call this signal that we have received, which is square root of 2 p cos 2 pi Fct plus theta, as a signal, and after that it would obviously be amplified by a certain factor. Please remember that this factor G is actually defined as the power gain, which means that amplitudes actually go as square root of G. Why do the amplitudes have to go as square root of G? Because remember that amplitude square is giving you the power, not the amplitude itself. So, if you want the power gain to be G, the amplitude better go as square root of G. Okay. So, this signal at this point is just whatever the signal that has come in, and this S of t is equal to square root of 2 p cos 2 pi Fct plus theta, but what you get here would be an amplified signal. Okay. This would be an amplified signal, but in addition to the amplification, you are also going to get a certain gain. Okay. So, this would be square root of G S of t, which is the amplitude of S of t that has been scaled up by a factor of square root of G. But in addition to that, you are also going to get a noise process. We will assume that this noise, which of course will have a much larger bandwidth compared to the signal, is adding to the optical signal. Please note that this is also optical noise. right, noise in the optical domain, this is also optical signal that you have, except that the optical amplitude has now scaled up by square root of g. The two optical fields are getting added. So, this model is sometimes called as additive noise model. Okay. In addition, if the noise process happens to have a flat power spectral density, then the noise is said to be white. In addition to that, if this flat or white power spectral density, the noise is also Gaussian distributed, then you talk about additive white Gaussian noise, and this is the model that we are going to use. So, our optical amplifiers are described by additive white Gaussian noise processes or additive Gaussian noise models. The noise adds to the optical signal. The noise has a very flat power spectral density, much larger than, ideally of course it will be infinite flat over the infinite frequencies, but for our purposes if it is flatter over the entire band pass filter bandwidth, then one can consider it to be white noise, and in addition to that the noise is Gaussian distributed. Okay. So, this is the AWGN model. What you have to take away is that after you have amplified the signal, you do not just get the signal, right. It would have been wonderful if we just had this as the output. Unfortunately, you have to also cope with the noise that the amplifier itself adds to it, right. And we have seen the reasons why the amplifier would add noise. The amplifier has spontaneous emission. Remember, the optical amplifiers are more or less like lasers, except that the feedback has been eliminated or the feedback has been made very small. There are still two processes, one is the stimulated emission and the other one is the spontaneous emission taking place, except that the stimulated emission dominates over here because you are sending in the external input signal. However, the spontaneous emission still keeps taking on. Okay. These spontaneously emitted photons will have a different polarization, they will have the random phase that is associated with them, with the result that the total field can be written as the stimulated plus the spontaneous one, and the spontaneous is actually a summation of certain random optical fields which have random polarizations. Okay. And then so you can call the polarizations as some EP. So, they have a random polarization. Of course, in this case it would be polarization as either X or Y polarization, but that itself is quite random. So, it does not, you do not know beforehand whether the spontaneously emitted photon would be X polarized or would be Y polarized. It would also have fluctuate in the frequency because it will have, although the center frequency would be Fc, because the amplifier itself has a wide bandwidth, it will have its frequency which is completely kind of fluctuating or changing. In addition to that, there is a different noise as well. So, you might imagine that the overall spontaneously emitted field could be written something like this, okay, where Fi stands for different frequencies within the bandwidth and theta I stands for the random phase that goes with that. The net effect of this spontaneous emission is that if you look at the process, spontaneous emission process itself, it would correspond to, in time domain, some noisy waveform. Okay. So, this is in time domain, it would correspond to noisy waveform, and all that is happening is thanks to this Fi and theta I. If you look at its frequency domain spectra, the noise actually has a flat power spectral density which is defined as N0 by 2. Please recall our discussion on the power spectral density that we talked about in the earlier modules. Okay, so, this is in the frequency domain, and because it is flat we call this as white noise process. Okay. So, at the output of the amplifier you have the signal which you want plus the noise which you do not normally want. Okay. Of course, you do not really want the noise to come out of the amplifier, but it is unfortunate that you have to cope with the noise. What happens after the band pass filter? Remember that the signal is centered at Fc and is usually having a certain finite bandwidth, right. So, if you choose your optical band pass filter having a bandwidth of B0, which is just enough to pass the signal, okay. Remember, the signal is coming from the transmitter all the way propagated through the fiber. Now, with the fiber you might actually see that fiber has both dispersion as well as non-linearities, with the result that the spectrum of the signal may not be exactly the same as the spectrum at the transmitter side. The spectrum would have slightly broadened, and your filter, optical band pass filter, should be sufficiently large to accommodate the extra broadening that the spectrum might have experienced. Okay. So, the bandwidth of the optical band pass filter is B0, which is just sufficient in order to handle all the information content within that. So, that is why we model this as a ideal band pass filter. After filtering, the noise would not be just n of t, it would be a different version, while the signal is more or less unaffected over here, because the signal, as we have said, is within the bandwidth, therefore, it passes through the band pass filter with very little distortion. We will assume no distortion here, but the noise gets filtered. Let us call that filtered noise as Nf of t. Finally, at the output of the photodetector, okay, so let me write down the output of the photodetector down here. What you would get is that you have square root of g s of t, which is the input signal or the information bearing signal, and the filtered noise. The photocurrent that comes out of the photodetector will be proportional to this particular factor, correct? It would be given by responsivity into optical power. Optical power in this case comes both from the signal as well as the noise. So, raising this to the magnitude square will give you the power, multiplied by R will give you the photodetector. This can be further filtered, okay, using the electrical filter EF. But let us look at what terms are you going to get here. Expand this magnitude square and you get one component here, which is g s of t magnitude square. The other component would be 2 square root of g nf of t s of t, and the third component is basically nf of t magnitude square. Clearly, this is just the signal component, and because this is signal multiplied by a signal or signal complex conjugate, we call this as signal and signal beating. This is just the noise, and the noise source for us is the amplified spontaneous emission source, or sometimes denoted by the spontaneous emission noise SP. So, this term is actually the SP, that is spontaneous emission noise, talking to itself or beating with itself. This is called as spontaneous beating term. Finally, you have a cross coupling between signal and spontaneous noise, which you call it as a signal and spontaneous noise. Our objective would be to try and look at all these terms individually and then find out the noise power and the signal power, so that it allows us to write down what is the signal to noise ratio of this amplifier. Okay. So, we are going to do that one. Please remember, these are just the terms that are coming out from the photodetector. Okay. After this, they have to be filtered further. So, we are going to look at what happens when you put them through the electrical filter later on. Okay. So, as a start, I would start with a slightly different version of the short noise that we have talked about. Remember short noise? Well, we talked about the short noise and we said that the power spectral density of the short noise, I am not sure whether we use the same notation as rho sh, but does not really matter. This short noise was given by 2q r p, where p stands for the optical power, times, so this is the spectral density, right. So, it was actually given by 2q into rp, right. So, this is the power spectral density. When you multiply this one through the bandwidth that you are looking at, that would give you the short noise power. Okay. So, that is what we had looked at, and the short noise spectral density by itself is given by 2q rp, multiply that short noise variance or the short noise power spectral density over the total bandwidth is going to give you the variance of the short noise. So, I think we had represented this as ISH for the photocurrent. We had represented this one as the variance of the short noise process, and that is the variance of the short noise process. Okay. So, this is what you are going to get. Now, our signal, or rather our optical field, actually has one short noise component sitting right because of the signal itself, right. Because there is a certain non-zero signal power, this non-zero signal power will in turn introduce a certain short noise component. However, these noise processes do not exactly look like short noise processes, because there is a cross multiplication of the filtered noise and the signal, optical information bearing signal, and this one is noise and noise beating. To understand and appreciate what actually goes on with those terms, let us completely forget about what we had learnt about the short noise. Okay. This following presentation is actually taken from a very interesting paper by two people, Rajiv Ramaswamy and P.A. Humblet. So, I would request, in case you have a little bit of a doubt over what we are going to talk about for the next 15 to 20 minutes, to have a look at this paper. This was in 1990, I think it was IEEE Journal of Light Wave Technology. I think it was crosstalk something, I do not exactly remember the full detail. I will post the links of this paper on the web page. Okay. So, whatever we are going to discuss is derived heavily from the paper that was authored by these two. Okay. The idea here is very simple. You have over time, so you have a time axis. Let us imagine putting up short windows of time. Okay. So, we want windows or intervals of time. These time intervals are all located at, say, this one is located at k times delta t. By this way you could have easily guessed that the width of each interval is delta t. So, every interval is the same width as delta t. Okay. So, for the kth time instant the width will be delta t, but the endpoints of this interval will be k minus half delta t, and this fellow is k plus half delta t. Okay. Does it make sense? Well, let us look at what happens when k is equal to 0. So, for k equal to 0 you are looking at a width of minus half delta t, or the endpoints of minus half delta t and plus half delta t. Certainly the width of this one is delta t, and t0, which is when k is equal to 0, which is t0, right, happens to be at 0th time axis, right. So, this is how we are considering these intervals. What is important is that one unit of this one does not really overlap with the other one. So, these are called as non-overlapping intervals. In this non-overlapping intervals, let us imagine that at each interval, okay, I am going to get some number of electrons generated. Okay. Where is this electrons generated? It is in the photodetector, right. So, let us say the photodetector, which of course has to actually look at the number of photons coming in, and each photon will generate a carrier based on the quantum efficiency of the photodetector, correct. So, if the quantum efficiency of the photodetector is eta, then for each photon that comes in, eta times the photon number would be the number of electrons or number of electron hole pairs that are generated. And these electrons, when they are generated, they will have to move to the one end of the other end of the photodetector material to constitute the current, and this process can be thought of as actually having a pulse that is emitted. Okay. So, this pulse, let us call this as some h of t. Okay. So, this is the basic pulse that is emitted. So, at each time you actually have some electrons that are present, there will be the number of electrons times this h of t. So, the basic pulse is also emitted along with that. At each interval you actually have different number of photons. Okay. So, at the k minus 1th interval you might have had n k minus 1. We will also assume that the number of electrons that are received or generated here, not received, generated here in the kth interval is completely independent than the number of electrons that are generated in any other interval. In other words, nk, if you consider this as a random variable, then nk and nl, where k and l are two different non-overlapping time intervals, they are considered to be independent. Okay. What would be the total current? Remember, this is just the number of photons that are emitted. So, the current itself is given by, it is the number of electrons times E, where E is the charge on each electron. So, this times E will be the number of electrons or the number of charge carriers that are generated, and these charge carriers are going to be traveling through the photodetector to constitute the current pulse. The pulse here itself would be shifted to the time k delta t, okay, because this is, we are considering the kth interval, and you simply sum this entire thing from minus infinity to plus infinity. So, this is how you can view the current, short noise current, that is being generated from the photodetector. Okay. But what can we talk about Nk? Nk is the number of electrons generated in time width of delta t, but this can be obtained as average number of electrons, okay, that are generated multiplied by time interval, right. How is this coming about? Well, you imagine that I actually take, I have made measurements. So, in the first in the 0th interval you got n0, in the minus 1 interval I got n minus 1, n1, n2 and so on. Okay. Now, if I take the time width that goes on for all of them, then let us say I do take a length of n, and then n times delta t would be the total time width. Find out what is the number of electrons that have been generated. So, here k will be equal to minus n by 2 to n by 2 minus 1, let us say. Average, or find out the total number of electrons that are generated, divide that one by the total time unit. What you get will be the average number of electrons that are generated per unit time, or this is called as rate of electron generation. Okay, this is rate of electron generation, and this rate times delta t is going to tell me the number of electrons on an average that are generated in that particular time interval. So, Nk can be written as the rate, which is lambda. Of course, this is a non-uniform thing, that is, in some, this lambda is actually a function of time, it is not a constant generation of the electrons. So, this has to be evaluated at the kth interval. What is the value of the rate at the kth interval, multiply this one by delta t, which is the unit width of the interval of the kth interval, right. So, this would be giving you the, this will give you the number of electrons that are generated in the kth time. But what exactly is the rate of electron generation? Well, we said that electrons are going to be generated depending on how many number of photons are converted into charge carriers, and that depends on the quantum efficiency eta. So, eta times the number of photons, which would be given by h nu. Please note that nu is equal to Fc in our case. However, I am going to use nu because that is kind of giving me the, h nu gives me the energy. So, that is something that I am used to. Okay. So, this would be the rate of electrons that are generated. You might have of course guessed that this can have been easily written as R by E, simply because R is the responsivity given as eta E by h nu, correct. So, eta by h nu is given by R by E. Therefore, you are comfortable in the fact that the rate at which electrons are generated actually depends on the photons that are being emitted or photons that are being received by the photodetector. Okay. So, with this, let us go back and substitute for lambda in here and rewrite the current equation. So, I have the short noise current, which is the photocurrent that is generated, given by E eta by h nu, summation k is equal to minus infinity to plus infinity, P of k delta t, and then you have h of t minus k delta t multiplied by delta t, because this is rate and rate has to be multiplied by delta t. Of course, this kind of is a summation over an infinite numbers, but you can get to a continuous distribution by taking delta t tending to 0. When you do that, what you get is the current I of t, given that a certain optical power has been transmitted. Okay. The average value of that is given by this limit of delta t goes to 0, because please note that this equation would be true only when you have received a certain power. If you have not received any power, then you have not generated any short noise. Therefore, the noise that you have generated when you go to the continuous domain is actually conditioned upon the fact that you have received an optical power. Okay. We will initially look at the current conditioned on the fact that you have received an optical power, or conditioned on the fact that optical power is non-zero and you have received it. Then we remove this conditioning factor. So, we remove this conditioning later, but with the conditioning and going from discrete to the continuous domain, when you apply delta t tending to 0 limit, this can be rewritten, the summation can be replaced by the integral, and the equation simply becomes E eta by h nu. We are assuming that these are all constants. Okay. Integral of p of tau times h of t minus tau d tau, where tau goes from minus infinity to plus infinity. Okay. Of course, there has to be an expectation operator. This is not exponent, this is an expectation operator. You can write down this current here in this particular way. So, this of course would be equal to taking the expectation operator inside and recognizing that the only random stuff that is coming here is from p of tau. E of p of tau would be the average power that you have received. Okay. So, this would be the average power that you have received. We will do this calculation slightly later, because more important than the mean, I am interested in the autocorrelation. Okay. The autocorrelation will be is defined as I of t1, I of t2 for time intervals t1 and t2, again conditioned on the fact that we have received a certain optical power. If we have not received an optical power, we would of course not be able to evaluate this expression. Okay. You can substitute you know from the previous this one. So, let us just look at what is I of t1 given t2, we can put in the expectation operator anytime we want. Okay. So, you go back to I of t here and this is I of t, here you substitute I of t1 and I of t2 and then multiply. So, there is going to be 1 delta t over here and this eta by h nu into p of k delta t is nothing but lambda, and you can write down the equations in this following way. So, you have E, before you go to the case of lambda, let us go to the first notation. So, I have to look at this short noise expression, evaluate at times t1 and t2, okay, which are considered to be 2 different times. Okay. There is no relationship between t1 and t2, later we will see that there is a relationship that we want to impose. Okay. So, here you get E of k n k h of t1 minus k delta t, okay, and you have one more summation coming from. So, let us also not put the limit delta t now itself. So, we will put the limit later. So, you have E L and L, this is because when you multiply 2 units, right, 2 things, you have to also take care of the cross products that can come in, therefore, you have to use another dummy variable L. So, you have N L h of t2 minus L delta t. Okay. This double summation, this is actually a product. So, this double summation can be written in 2 terms, one term when k is equal to L and the other when k is not equal to L. So, when k is equal to L, you have E square, summation is still there, but k, and remember k is equal to L, and you get n k square because k is equal to L here, h of t1 minus k delta t, h of t2 minus k delta t, this is first term, plus you have one more term which is E square again because you have that, and the double summation continues k into L, you have n k n L h of t1 minus k delta t, h of t2 minus k delta t. Okay. Clearly k must not be equal to L in this second expression. Now, we are ready to put in the expectation operator. So, if you put in the expectation operator onto this one, you see that the random variables are coming from nk. Okay. So, you get 2 variables, E of nk square and E of nk into nl, and we are going to discuss this one. So, the discussion continues in the next module. Okay. Do not go anywhere, we are going to look at the variances of each of them and then talk about what happens to the autocorrelation of the current. Thank you very much.